We have been traveling from modules 1 and 2, which were mostly about empirical research, through to module 3, which was more about reflections coming from more empirical research. And module 4 is going to be about thinking about the place of quantitative reasoning in education and a more theoretical view on reasoning quantitatively and the use of numbers, with a final piece of research on work done with teachers. Now, before we move forward, I want you to imagine one of these early evenings when you were walking somewhere or driving somewhere or looking out of the window and you saw this enormous moon rising in the horizon. It is something magical that many of us have experienced, and probably not just once. Now, here's a comment by Richard Gregory, who was professor of neuropsychology in Oxford University. To the visual part of the brain, the moon is a few hundred yards away, as you just imagined it. To rational thinking, the distance between the Earth and the moon is about 380,000 kilometers. How is this possible, that what we know is not what we see? Psychology, in its beginning, was very interested in understanding visual illusions. And this is a visual illusion that many of us are likely to be familiar with. It is called the Miller-Lyer illusion. And we all know that the segment between the two arrows on the left segment, is the same size as the segment between the two arrows on the right. We know it, but that's not what we see. So when we know is not what we see, how is that possible? It is the power of forming reasoning systems that go beyond our perceptual systems that allow us to know what we don't see. So the first psychologists were interested in how it is that we step outside illusions and the role of measurement and rational thinking in overcoming illusions. Not in the perceptual sense. We continue to see something which we know is not true. The problem that psychologists then became interested in solving is, how do we learn the meaning of numbers, and how do we learn about measures? There are two very different views on how we learn about numbers. Well, there is a variety, but there are two families of theories about how we learn about number. One is what we call the associationist view. And the theory holds that a child learns the meaning of number words because they hear the words and they see objects in a specified numerosity. So if a child sees 3 dots and hears 3, or 3 rabbits and hears 3, or 3 children and hears 3, then the child learns the number of 3, the meaning of 3. And if a child hears 4 and sees 4 ducklings, or 4 cars, or 4 pencils, the child learns that 4 represents that numerosity. A major difficulty of this view is that there is no principled connection between the numbers. The meaning of 1 has absolutely nothing to do with the meaning of 2, which is also completely independent of the meaning of 3, and so on. There is absolutely no connection, no principled connection between these these different numbers that indicate different numerosities. There is a second family of theories that is called the representational view, and this is a radically different theory of how we learn the meaning of number words. The idea is that a child learns the meaning of number words when the child realizes that as each object is counted, it is added to the group of already counted objects. So 1 is this, and that could be learned by association, it doesn't matter. But then the child only understands the meaning of 2 when the child realizes that a second object was added, and the same is true of the meaning of 3, and the same is true of the meaning of 4, and so on. So according to the representational view, the meaning of numbers, of natural numbers, is relational. Each number is equal to the predecessor plus 1. So what's important in the representational view is not the particular quantity, but the relation between that quantity and the preceding one. It is a very different theory about the meaning of numbers. And the extent of this difference we can explore briefly in some examples, which I will be discussing next. Now, in both theories, numbers are cultural tools, and they are words in a system of signs. But in the associationist view, the only relation between the numbers is that one is after the other. So when you learn to count, you count a string, and that's what people talk about, knowing the counting string. So you know the order 1, 2, 3, etc. But that's only the order of words. It has no relation to the meaning and the world itself. Now, when we think about the representational view, there are actually two kinds of meanings for number words. So the signs, the words, represent something. So when I say 5 rabbits, I'm referring to a specific collection. When I say 3 monkeys, I'm referring to a specific collection. So this is the representational meaning. But there is an analytical meaning of numbers, which is given by the fact that numbers have a relational meaning. They acquire, 2 acquires meaning when the child realizes that 2 is obtained by the addition of 1 to a set, to a group of 1 that was already there. So this brings us back to the idea of schemas of action and to the idea of addition as an important schema of action for natural numbers. The meaning of rational numbers is different, but unfortunately, I won't be discussing that in this presentation, although I will have at the end a reference that discusses this specific topic. So when you start from a representational view that includes the concept of addition into the meaning of numbers, of what numbers represent, you can see how it relates to the analytical meaning, because numbers are systems of meanings that are organized by operations, and natural numbers are organized by the operation of addition. When we understand the analytical meaning of numbers, we can form reasoning systems that go beyond the information that we had to begin with. So let's think of an example of what I'm saying, because I think it's much easier to refer back to this example and then think about the analytical and referential meaning of numbers. So imagine 3 children, Sam, Charlie, and Ali. And if I tell you that Sam is older than Charlie and Charlie is older than Ali, you don't have any numerical information about these children, but you can use the quantitative reasoning that you have and conclude that Sam is older than Ali. So this is a quantitative reasoning based on order. Now, let's think about the next example. Here are the children, Sam, Charlie, and Ali. But now what I'm telling you is that Sam is 10 years old, and he is 2 years older than Charlie. And Charlie, in turn, is 1 year older than Ali. Now you know that Ali is 7 years old. So you used your quantitative reasoning about order, you used your quantitative reasoning about addition, and you used the analytical meaning of numbers to reach this inference. So when we know the measures, our reasoning about quantities is empowered. And our reasoning about quantities comes, if we refer to Thompson's definition, for our ability to reason about relations between quantities. Now let's take this thinking a little bit further, and we're going to think about relations between quantities. I want to start from the situation. In a class, there are 24 children. There are 8 copies of the same book that the teacher wants the children to read. Now, 2 different scenarios. The teacher wants to know how many copies of the book she needs to buy so that each child has a copy. But the head teacher wants to know how many children have to share a copy before she decides if she's going to buy more books. So the teacher and the head teacher have different questions, so they have to establish different relations between quantities. So relations between quantities are not objects in the world. They're not right or wrong. They are established by people when they want to answer a question. We can establish different relations between quantities when we ask different questions. In order to reach a good answer, we have to establish the right relation between quantities. So the teacher has to establish an additive relation between the quantities. So it's a part-whole relation that she needs to establish. What part of the children won't have any books once we give out the first 8 books. But the head teacher wants to establish a ratio relation between children and books. How many children per book do we have? Now, I'm quite sure this seems very elementary and very simple, but this example is about thinking that establishing relations between quantities is an action of people when they're trying to model the world. The relations are not in the quantities or between the quantities themselves. They are part of what people do when they are trying to solve a problem. So the schemas of action that children have, joining, separating, comparing in one-to-one correspondence, setting in one-to-many correspondence, these are all options of what children could do if they had objects to model quantities. The question is, how do we help children understand which relations are relevant for which kinds of questions? In testing the elements of this theory in action, we decided to develop a program for teaching mathematical reasoning in primary school. We started from the idea that children can be taught about mathematical reasoning from the beginning of elementary school if they are taught to use their reasoning in action, and that teaching arithmetic as reasoning about numbers also promotes children's mathematical development. And the third point of this program is that additive and multiplicative reasoning need to be distinguished from an early age so that children form reasoning systems using different schemas of action for additive and multiplicative reasoning situations. Using this theory, we developed a set of materials to support teaching so that teachers could draw on this material to work with children in developing their quantitative reasoning and in developing their thinking about numbers. The teachers were prepared to use these materials by having professional development sessions with us, and we redesigned the materials and the teaching in an iterative way. So every time we worked with teachers, we reflect on how the teaching had worked. Tania Campos is a good friend of mine who led a professional development program in São Paulo, and she saw teacher education as crucial for educational change in mathematics. And as I discussed in Module 3, we had studied the work of Lieven Verschaffel and his colleagues that suggested that we really needed to change the way word problems were seen and thought about in elementary school. So we created a project that was called To Teach is to Create, because it aimed at both creating new ways of thinking for children and new ways of thinking for teachers. And we tested this program originally in São Paulo. During this program, we engaged teachers in thinking and talking about quantitative reasoning, in trying activities in the classroom, and coming back after they had tried out these activities and presenting them to each other and to us, and recording and analyzing data from their classrooms so that we could have a case study of how the classrooms were developing. In this program with Tanya, we learned about teachers on quantitative reasoning, engaging them in discussing alternative theories of how to teach mathematics to primary school children, and in collecting and discussing the evidence from their classrooms. We constructed new knowledge alongside the teachers, and we actually wrote a book for teachers on this project. The question is, did the project work? Did the children who learned, who received the program, make more progress in mathematics than they would have normally in the classroom? We were able to address this question many years later when the Education Endowment Foundation in the UK funded an evaluation of the mathematical reasoning program. The Education Endowment Foundation engaged an external evaluator to choose a test, randomize the classes to different groups, a comparison group and a taught group, and to assess the children before and after the children had engaged the program. This was a large-scale study that involved a total of 37 schools and 1,365 children, and the children who were in the taught group participated in 12 weeks of teaching once a week dedicated to the mathematical reasoning program. One can think that to some extent this is a very small amount of teaching, 12 hours in total, but from another perspective, this is a very good amount of teaching because it reoriented the way the children thought about learning mathematics in the classroom. They had the experience of starting from schemas of action and progressively taking counting and arithmetic operations as part of the reasoning systems that they were developing in action. The outcome of this large-scale evaluation is that the children who engaged with the mathematical reasoning program made an additional 3 months of progress in mathematics in comparison to the untaught group. So to conclude, the theory that we developed from the work on street mathematics alongside the work on school mathematics, both by our research group and other research groups in the mathematics education community, was transformed into action by a program in which we worked with teachers. The teachers worked with the children, and the children were able to achieve more in mathematics by the standards of school mathematics when they had been engaged with this program. Just before we finish, I want to reflect a little bit on my learning trajectory. The presentation in these modules was basically inspired by psychological theories, but in fact, the research that led me to the ideas came both from psychology and from mathematics, and actually also from mathematics education, from pedagogy. Research on mathematics education was crucial for the development of the theoretical approach that we achieved on understanding children's learning. And it is the collaboration among disciplines in the study of how children learn mathematics that has been a very rewarding experience for me in the 30 years that I've been doing research on how children learn mathematics. My hope is that these ideas can offer some contribution to teachers and teaching in the future and to further learning about how children learn mathematics. I will leave you with some references, and thank you. You have completed my unit of the ICME AMO.